Hello everyone, good evening. So I'm Harini Gunabalan and I'm a student from Technical University of Darmstadt. I'm majoring my master's in distributed software systems. And thank you GDG and TechEds for offering me this opportunity. So today I'm going to talk about machine learning with the TensorFlow library. So let's look into the basics of machine learning. So what is machine learning? So machine learning is this field which it's a subfield of artificial intelligence basically. And we have used it extensively for a lot of computational theory problems and pattern recognitions. And it's very useful to make a lot of prediction algorithms, like to solve problems which needs prediction, etc. And we can also find a lot of hidden insights from the data where programs have to learn by itself. Like machines have to learn by itself rather than explicitly programming them. So we look into examples to get a better insight of what type of problems machine learning could solve. So some of the examples are like the applications that cannot be programmed by hand, which is like self-driven cars, automated helicopters, etc. So these, for implementing these type of applications, the machines need to learn a lot of how it works, etc. So these type of problems can be solved. And also, another two subset problems which could be solved are like the database mining. So nowadays we have Google Analytics, which has a lot of click streams of data, and it can predict the user behavior based on these data. So this, and also the medical records like the DNA, genome data. So it's machine learning is used extensively in these fields. And most of us have used Amazon, etc. Right? Everybody use it. So we've seen the product recommendations which we get usually, and this data is all machine learning is used extensively to predict these type of data. So what's the process? How exactly machine learning is done? So it consists of two main phases. The first phase is the learning phase, and the second phase is the prediction phase. So in the learning phase, we first create a model. The output of the learning phase is a model which is used by the which is learned by the machine. So we give a training data set. In machine learning, it's also common to split the data set as the training data set and the testing data set. So using the training data set, we create the model. And in the second stage, the test data set is actually passed to the machine. It uses the model to come up with a prediction, for example, a prediction, etc. So now let's look into the types of machine learning. So it's broadly classified as supervised learning and unsupervised learning. So first we'll look into what supervised learning is. And underneath supervised learning, there are two types of problems which it usually solves. It's called classification problems or the regression problems. So in the case of supervised learning, the main difference between the supervised learning and the unsupervised learning here is in supervised learning, for example, if the input image, if this image is given to the machine, it also the data itself is actually given to the machine, which means we specifically tell our machine that, hey, this is number 5, you need to learn it. So we'll give you a lot of data like this. So the machine eventually knows how number 5 is written, like a handwritten, recognition of handwritten images. So now let's see examples of regression problems and okay, this one is a specific, like a block diagram, which gives us clarity into how supervised learning actually happens. So if we notice, one major, very important thing to notice is the labels which we give here. So using the training data set, the machine uses a lot of features, etc. and the machine also is given labels as the input. So based on that, the output is later predicted for the testing data set, and the output is usually like the expected labels. Now let's look into the regression problem. So what exactly is a regression? In regression, the data the target variable which we are looking is usually continuous. For example, we have this problem called the housing price prediction, where we have a house, the house is the size of the house in square feet, and the prices are on the y-axis, like in dollars. So the plotted data is actually the data of a city in the US, and if we see that, for example, I have a 750 square feet house, and I want to know I want to know the predicted amount if I want to sell the house. So based on the data collected, for example, if I have an algorithm which has come up with this pink line, then it's predicted that my I can sell my house probably for around $150,000. But in case if I have a better algorithm which predicts it in a better way, as we see in the blue graph, then it's more accurate and it shows the value of $200,000. So this type of problems where the target variable is going to be continuous is known as regression. On the other hand, we have classification problems as well. So for example, the classic classification problem is cancer type prediction. So in the first case, when we consider tumor size as the feature, when the tumor size is up to a certain limit, we can surely classify it as a benign or a mild type cancer. But if the tumor size is beyond a certain level, then we are sure that it's going to be a malignant type of cancer. But of course, there is some area in between where it's a little bit blurry. So in reality, for problems, we need to consider more features. Like in the second case, we consider tumor size and age of the patient as the second feature. And we also see how the machine ultimately does a classification. Like this is almost like a line, so it's like linear type of classification. But in reality, the good part of machine learning is that it can handle infinite number of features. So like tumor size and age, even if we give an infinite number of features, we have algorithms nowadays to handle that. So that's about classification problem. Now let's look into what's unsupervised learning. So here the difference is that we don't know what is being the input. The machine does not, we don't tell the machine explicitly that this is exactly the data which is being fed in. So it's up to the machine to learn the data, to look into the data, several features. It looks into a lot of features and clusters them. So here the machine uses clustering algorithms basically to cluster the data in such a way that the machine itself learns from the features and categorizes it into several clusters. So for example, we have the Google News, which uses this. And if we see, notice like, for example, there is about, the news is about Paris climate conference. So all the data which is available, all the blogs which are available, the machine is smart enough to identify that this is under this category, and it classifies the several news. So you also use this type of unsupervised learning in social network analysis and many more examples. So here we see that there are no labels being given to the machine, and the machine ultimately has to predict like the cluster to which it belongs to, cluster to which the data records which we pass actually belong. So the second part of my talk is about TensorFlow. So what's TensorFlow? It's an open source machine learning library. It's developed in C++ and Python, and it's originally developed by Google Brain team, which is inspired by how the human brain works. So we'll look into the details of what this library has to offer us. So what's a tensor? A tensor is an n-dimensional array. So for example, it could be, if it's a one-dimensional, it's a one-dimensional vector or a 2D matrix. In our case, we can represent an image as a 3D tensor with the row and column for specifying the pixel, whether there is a pixel on that particular point, and the third dimension could be the color as well. We will also be looking into how this is represented in the next few slides. And so the data is the tensor, and the flow is ideally the operations which are going to be acted upon these data. So so basically the nodes and edges of this TensorFlow data flow graph is going to be the nodes would be the operations, and the edges are the data on which these operations are going to be acted upon. So let's consider the MNIST example. This is one classic example. So MNIST is a data set which has a number of images like what we see here, 5041. It's like handwritten images, and we're going to train our machine to identify the handwritten image. So in order to do that, initially we separate the data set as the training data set and the test data set. The training data set consists of around, for example, 55,000 records. And for instance, like we split about 10,000 images to be the test data set. Now we're going to consider that each data set will have the image part, which is Xs, and the label part, which is Ys. So the image part is represented as a 2D tensor, and the label will be the actual value, the actual number on the image which we see here. So if we look into this particular image, so this is 1, and this is how the matrix, 2D matrix is going to be represented. So it's in this case, it's represented between 0 and 1, with the probability that if it is 1, it means the particular point there definitely has a black dot, and if it is 0, then it means that there is nothing there. And if, for example, like if it's a little blurry, like how it is in the edges, then we represent it with the probability values accordingly. So how each of these images are going to be represented is, for simplicity, this is actually a 14x14 matrix, but in reality, in the MNIST, in this example, it's going to be represented as a 28x28 matrix. So ideally, each image will be considered as an array of 784 points. So since we classify 55,000 training data set here, so this tensor, the image tensor Xs will correspond to this 55,000, 784. And the labels. So we also need to know, we are feeding the labels to the machine. So we feed the number, for example, this image is 5, and in this case, this image is 1. So the label, we tell the machine this is ideally how one is going to be. So, and we use these two terms called softmax regression. So softmax regression, as is basically a function which is going to be represented, which will classify the input data set based on the probabilities. So if we pass an image 8, and it would probably be expressed as 80% it is sure that it's 8, 5% as it's 9, and maybe 1% that it's a 0, etc. So this softmax regression is a function which would eventually show the classified label in percentages, and the one which with the maximum percentage is taken by the system, by the machine, saying that yes, it's an image 8 or etc. And we also have this term called cross entropy, which is going to be a measure of actually how bad the model which we've created is. So when we train our machine and also give the testing data to verify that, if our machine is classifying the data in the right way, we need to measure how well the classification of the data has happened. So in order to do that, we use the cross entropy term using this formula, where the y is the predicted distribution of our testing data, and y dash is the actual distribution. So we get to know how well the machine has classified. So this is like the block diagram of how the softmax regression works. So using W corresponds to the weights and B is the bias. So using these values, each of the input data set is classified into a label with a percentage. And ultimately, the one with the highest percentage is considered as the data set is considered to be under that particular label. So now let's look into a demo of this. Thank you.
Who here has tried TensorFlow for the first time? A little. Did anyone try it out yet? No? One. One tried it out. So. So to say again what she's going to do, she's going to try to show you an actual presentation of how the MNIST data set, of how this example of machine learning can be represented in TensorFlow. And actually, I saw her talk yesterday, so I know a little bit more than you do. And she's setting up the environment right now. And now she should be able to show you how it's done. So basically, the TensorFlow library, as she said, is written in C++ and Python. So the core is written in C++, and Python is the user interface. And she's going to take it away.
Right now, I've just installed the TensorFlow libraries, and I've activated my virtual environment inside. So we're going to run a small Python script. Initially, I'm importing the data which I'm going to use. So this is my testing and training images from the MNIST database dataset. And
55,000 images?
Yeah, actually 60,000, roughly a little bit more. But for testing purposes, I won't be actually using all the 55,000, but we'll see in the code exactly how the images are taken. So now this is going to be the most important part where we are describing our model. So the formula for the soft regression, the weights, biases that we saw. So we have the input x, the weights and biases as well. And now we define that the y value will be w times x adding b. And we also define the the formula that we saw in the slides for the cross entropy. And this step now, the one which I'm going to show now, this one, is the place where we actually training where we actually give the train step. So this is like the gradient descent optimizer. It uses this function, which is a part of the TensorFlow library. And we also give the input to minimize cross entropy, which means for the machine to be, we need the machine to be as smart as possible. Cross entropy is a measure of how bad the system is. So we want to make the system as good as possible. So let's initialize all the variables that we created. So, and here, ideally, I'm going to actually give the data for training the machine. So one thing that we notice here is we're actually not giving all the 55,000 images because it's a huge amount. So in a better way to efficiently do this, they are taking 1,000 times this loop runs for and each time the loop takes any random 100 images and then processes this. So it's like to make the system more efficient by taking any random 100 images out of the 55,000 training data set. And now we can see how accurate our system has predicted these images by these lines. So what we see here is a 0.91 accuracy. So this is roughly like around 91%, which may seem to be good for now. But ideally, there are much better algorithms which take the efficiency for up to like 97% or even 99.9%. So this one which we've done here is like the simplest of every algorithm, and it's the basic one to understand and learn how we do it. And there are also many more algorithms and many more algorithms. And in the TensorFlow page, like this TensorFlow.org website, there are many more tutorials to understand this better and go ahead with further higher level algorithms. So thank you everybody. Any questions? So,
Yep.
yes.
Can you comment on any differences or commonalities to other libraries like scikit-learn?
Well, I honestly I haven't used those for me to find the difference. But what I was able to figure out after using this library was, I thought mathematically, like implementing each of these would it would be impossible for me. But all it does, it was like one line of code which actually did it. So the library has many things like this, and the good part is we can maybe use it in our daily applications, etc., in our simple applications, and it's also across, like it works in Android and desktops, distributed systems, etc. So, yeah.
Is the image functionality, so the analysis of images, is this built in or is it like an extra library?
The image database is something which is hosted. I had to download this image database. It's called the MNIST database, which you can find it hosted on online. If we see this TensorFlow.org, they've given a link to download the dataset from. So that's a separate dataset.
I mean the analysis of images.
Yeah.
Is this like a separate component? How good is it? I mean,
It's not a separate component, like what exactly, like, because in the data set that we download, we also have the weights and biases. So using that, it identifies that's how the image is classified, yeah.
so you can just put in random images. That's not going to work.
Random, this is basically just for the handwritten images, and this is a very simple data set which was only for the numbers, digits. We have like ones for alphabets, and there are some small image data sets to identify if it's a cat or not a cat, etc. Some simple things like that. So
This image data set needs to be like special annotations or something like that. I don't know.
no, it's not any special annotations.
Because it's not like the program knows what's on an image, so you have to say,
Yes,
okay,
yeah, the program.
I know how do you describe that?
Well,
it's
that
maybe a
was-
stupid question, but
but that's
seems-
how that's what this the model that we created, because the machine does not know anything about the data set. That's right. So it almost looks like a magic. Like, how did it figure out? Because that was like the model, the simple formula which we used, the Wx plus b, and to calculate the entropy. So using that, they have come up with this algorithm to figure out how the image can be processed and how the machine can know what the image is. Yes.
Another question?
A very practical one for me. The MNIST dataset is pretty localized to American handwriting. Like the 7 doesn't have the
Okay,
line, like
the
we
line.
Germans write it. Do you
Yes.
know about any German training sets?
Maybe, yeah, the ones with the umlauts, right? And I don't know for alphabets. But maybe I think I should look into it. I can maybe check if there are some better data sets to have a global mixture of, all over the world. And I can probably check that and let you know. Sure.
Thank you. I mean, I've heard about TensorFlow before this talk, and I heard that they're open sources very recently. And I also heard that they are supposed to be like 5 years ahead in their, artificial intelligence learning technology. That's why everybody's so excited about TensorFlow. And I guess they're using something like, which is called deep learning in their machinery. Can you tell us something about what does this magic? What is so special about TensorFlow compared to others?
So there is this. This is the TensorFlow. Is from what I read, it's the second generation from Google's deep learning team. So they are a group of technologists, which is called the Human Brain Team at Google Brain Team. So they released a first generation open source model like TensorFlow, but that was too big, and they found that it was like not many researchers were able to use it because of the complexity. And what TensorFlow offers here is much like a simplified version, which could especially used by researchers, students who wants to find an immediate impact. And I also heard about this deep learning technologies which they're using, like for example in the Google Now and all those latest applications. So they are probably like the Googlers would probably be way ahead of what they have released to open source. But this is the base of what they're using. So using this, maybe a lot of students and researchers could come up with better, good implementations or good usages in their applications.
So basically, they built on top of years and years of their knowledge of machine learning. So they hadn't TensorFlow before.
Yes.
They developed it because they tried to get the software.
The first generation one was called something else, not TensorFlow, but this is the second generation one. And the basic idea for them to release this as OpenFlow is to make use of the machine learning ideas which they are using in our applications as well. Not just in Google Now, maybe there could be someone who's coming up with a personal assistant like something like Siri or Google Now. Yeah.
So they released TensorFlow, but they didn't release the data they used to train their servers, of course. Yes. So, and that's the magic behind machine learning. Because machine learning, whatever you do, the data which you put in, for example, like the German 7 and the English 7, is essential for the machine learning what's there.
Yes,
so if you put it, if you put their images like cats and non-cats, then maybe you can decide if an image has a cat or not a cat. But maybe you want to do it to a bit better purpose. Yep.
How many images? But this one had around, the thing is like, if we notice, it totally depends on the input data which we are giving. And in our example, we used it for like 1,000 loop runs of 100 random chosen images. So if we have a data set which is going to be like a bigger one to train it, then obviously the results would be better, I assume. So it's up to the data set that we use. Yeah, maybe I think going up to like 100,000 would make the system a better one, like would train the machine in a better way. Yeah, roughly.
Okay, last question. I see, and he was the first.
Okay, looks like.
Yep.
Okay.
As I understand you, in the TensorFlow, you apply the same algorithm to a particular data set and then try to classify images from another data set using always the same algorithm, or you at least for a given class of problems.
Yes, yes.
Are there attempts to adopt the algorithm automatically according to the problem? to change the algorithm?
I think that this would be up to our usage, like what is the ultimate output that we need. If we choose to, for some cases, as I mentioned, like a 90% accuracy would be good enough, but in some cases we need to have more accurate and perfect results. So in that case, we need to move to different algorithms, which gives us better results. Oh. Okay. Well, yeah, not that I'm aware of, but maybe it would be a good idea to choose the algorithms. Could be like a good idea, but not, as far as I know, there is nothing that is already automated, I guess. But maybe like at Google, like how it uses in their, how they use it in their applications, they might have something like this, like what you're mentioning, to automatically choose the algorithms.
So I think basically you can emulate a first step of this. So basically TensorFlow has lots of algorithms to work with, and obviously she only tried out one. And in the end, you get a percentage of how good the model performed. So you could just try out and say, oh, I'm trying out these 100 different algorithms, and then you pick the best of what fits your data. So this is, of course, a valid approach, but as she said, I don't really know if they are working on really evolutionary algorithms. Yeah, talk about Skynet. Evolutionary. Okay, I think that was the last question. Thanks again, Harini, for the machine learning talk.